Now we are going to discuss what we call the cross field. It has a lot of application. One of the application is velocity selector, and we are going to talk about this now. Here in this, where the cross field, here the magnetic field, which is B, as you know, and the electric field, which is E, as you know, are perpendicular. So I'm going to apply the two fields. They are perpendicular, okay? I'm going to apply the two fields now, the electric and magnetic field. So, according to your knowledge up to now, if you apply the two fields on a charged particle, it means you will have two forces. One of them is the magnetic force, FB, which is QV cross B, and the other one will be FE, which is Q times E, okay? So you will have the two forces, because I'm going to apply a magnetic field B and electric field E, which are perpendicular to each other. And let's look at this situation here, okay? Let's do it on the plane. Okay, on the plane. So let's imagine that the magnetic field is inside, okay? That's in. The vector is in, magnetic field is inside the board. And my electric field is downward, okay? And I have a charged particle, let's say a positive charged particle. Let's imagine that the particle is positive, okay? Plus Q. Plus Q, the charge is positive, and moving to the right. You need the velocity for the magnetic field. Eh? For the electric force, you don't need a velocity, but for magnetic force, you need a velocity. So it has to have a velocity. If the particle doesn't have a velocity, the only force will be the electric force, okay? There will be not two forces, but now that I have two forces. My son, I want you to draw for me the two vectors, two forces. Let's look at the electric force, because it's easy to find. And the electric force, you look at the sign of the charge, you look at the electric field, the electric force will be downward, like this. Okay? That's the electric force. Force, F. Electric force, F. Let's write here Fe. Okay, F. That's Fe. Okay, Fe. That's the electric force. It has the same direction as the electric field because the charge is positive. Now, how do we find the magnetic force? Now, remember that B and E are perpendicular to each other. B is inside and E is down. So, inside and down, the angle between them is 90 degrees. You can see it. This is inside, and that's down, and the angle between is perpendicular. They are perpendicular to each other, okay? So this statement is correct here, in this figure here. Now, show me the direction of the magnetic force. Okay? Your fingers are what? With V. And B is inside. So you sweep like this. That's the magnetic force. FB. What do you notice, my son, here? The two forces are opposite. And the charge and the particle is moving to the right. So, you have three situations. So we have three situations. Three situations. Either if the first one is FB is greater than FE, it could be that this force is greater than this force, so the particle is going to go this way, like this. This is the trajectory, yeah? Trajectory. Because this force is higher than this force. So you draw the positive charge here, this force will be like this, and this will be, so this is FE and FB, so the net force will be up. Net force will be up, and it will take the particle this way. Now, if FB is less than FE, okay, this force is bigger than this force. The particle will be going like this. So let's draw the particle here. That's FE, and that's FB. So what is the direction of the net force, my son? Here, the net force will be downward. So the particle will go in this way. This is the trajectory of the particle. Now, what happens if FE or FB is equal to FE? Is equal to FE. The two forces are equal. What happened now? If the two forces are equal, the particle is going to move what? In a straight line. So the particle will go in a straight line trajectory, okay? With what? With a velocity v, constant. Okay, that's the direction of the particle. The two forces cancel. Here, now let's look at this v. I'm interested in this v here. Okay? Look at when FB is equal to FE in magnitude, it means QVB, right? What is the angle here between V and B? I want the angle sine theta, sine theta. This is V and this is B. V is outside and B is inside. What is the angle between them? It's 90 degrees. So sine 90 is 1. And this is equal to Q times E, which is the electric field. So I can find the velocity or the speed of this particle is E over B. Okay? So people, what they do in this case, this is called the velocity selector, okay? What do they do? They play with the electric field and the magnetic field. They can, okay, so they play with them so that the ratio, so they can find the speed of the particle. If I know E and B, if I know this value, okay, and I know this value, I can find this, okay, find V, knowing E and B, all right? Okay, we are in this situation here. If I know E and B, I can find V, so I can select the velocity or the speed of the particle. I can play with the value, so you can play with the value of E and B such that V will have a certain value. So this is called the velocity selector. Right? It's called the velocity selector. The velocity selector is always when you have in this situation here, where this is number 3 here, when the two forces are equal. Okay, my son, let's apply what we have learned here to this small example here. We have four cases. I'm showing you the magnetic field direction, the electric field direction, the charged particle with the velocity v direction here. This means the electric field is outside. This means B is to the left, and the particle is moving to the left. Can you tell me what is FB in this case? What is the magnetic force? Magnitude and direction. In this case, number 1. Since V and B are in the same direction, there will be a sign of 0, which is 0. So FB is 0 actually in this case. Because if you go here, because I remind you that FB is QVB sine theta. Sine, the angle between V and B. Here V and B are in the same direction, so the angle between them is 0. Sine of 0 will give me 0, so FB will be 0. And FE in this case will be in which direction? FE, positive charge, and FE will be in the same, first of all, it's Q times E, right? That's the magnitude of it. And it will be outside the board. Outside the board. You agree? I hope you agree with me because this is a positive charge. So F net in this case, F net, which is the sum of them, you see here, F net is in this direction here because FB is greater than FE. Here F net is down because FE is greater than FB. F net here is 0 because they are equal. So F net here is equal to what? It's Q times E only because FB is 0. Let's look at this situation here. And it is outside. Okay, out of the board, because it had the same, it's this case here, okay? Here, how much is FB in this case? FB here is also 0, but the angle between them is 180, so sin 180 will give me 0. And FE is equal QE, and still it is out. So here F net, when you add them, F net will be QE and out, okay? So this situation, these two situations are the same. This situation 1 and 2, they are the same, okay? Let's go to this situation number 3. Here FB will be what? FB will be, now the angle between B and V is 90 degrees, so sin 90 will give me 1, so it will be QVB. Give me the direction of the force here. Look with me here. My son, look with me. V is in this direction, B is what? To the left, so my force will be out. So this will be out. Okay, out. Outside the board, okay? Now, look at now the electric force. Fe is Q times E But because the charge is positive, it will be the same direction as E, which is out, okay? So the force will be out. So what will be F net here? F net will be Q VB plus QE, because both of them are out, so you add them, okay? You have to add both of them now, in this case. Let's look at the last situation here. What is FB here in this case? V is down, B is to the right, so you do like this. B is down and V is to the right. So V is to the, now this is V and this is B. V is down and B is to the left, to the left, so my force will be in. My magnetic force will be in. So it will be Q, V, B, inside. Inside what? Inside the board, eh? And FE, I don't think FE will change because this E is always out, so my FE is always out, eh? So it will be QE out. That's the direction of it, eh? Now, what will be the F net? In this case, it will be QE minus QVB. Why did I put a minus sign? Because this is inside. We take by convention any vector inside negative, outside positive. So this is my F net, and I don't know what is this. What happened here? The direction of N net I don't know, and this I put numbers here. If my calculation here is positive, it means F net is outside. If my calculation here is negative, given the value of the different things here, if F net is negative, it means inside. F net is positive, it means outside. Okay, now we are going to discuss the concept of circulating charged particles. So these are charged particles, positive charge, let's take, and they are in magnetic field in this region, which is coming out of the board. So I know the magnetic field is out, the velocity is up. So can you tell me what is the direction of the force, magnetic force, on this charged particle by using the right-hand rule? I give you 30 seconds to think about it. What is the direction of the magnetic force, FB, which is Q V cross B, okay? We call this Lorentz force, okay? Lorentz is the name of a physicist. So what is the direction of this force here? By using the right-hand rule. So you put your fingers with V. You can put like this, but when you sweep, it doesn't take you to B. B is outside, huh? You can do like this. When you sweep, it doesn't when you sweep inside, so B is outside. You do like this, okay? You have to do like this. V cross B, because B is outside. At the end, your finger should be in the same direction as B. Beginning V and B. The force is in this eye. So the force is in this direction here. That's FB. And the angle here is 90 degrees, because V and B are perpendicular, okay? We said that V has no component along FB, remember? 90 degrees between them. The component of V along the FB, there's no component, zero, okay? Now, you have done in classical mechanics, when you have a particle moving and the velocity and FB are perpendicular to each other, you get this kind of motion. Okay? Alright? Now, the particle is here now. Be careful, huh? The particle is here, and its velocity is to the right, because, okay, to the right, that's V. Give me the direction of the force there. Okay? B is out, eh? Remember that B is out. So, V cross B, the force is down. That's FB. We are applying now the right-hand rule many times, okay? Now, V and B are perpendicular, it will be moving in this arc here. It will come, and this location here, and this is, let me draw correctly, yeah, you make it correct here. So it will come here, okay? Then my particle is here, positive Q, okay? And what is the direction of V? V is down in this case, because it's moving the particle. V is down. V is always tangent to the path. Tangent. What will be the direction of the force here? V cross B. The force is in this direction here. Okay, what do you notice here? The force is always to the direction of a point here, which is so this will be, at the end, it will be a circle. So this is a circulating, it says circulating charged particle. The particle is moving in a circle, when a particle comes here, at this location here, plus q, the velocity will be tangent to the path. It means to the left, that's v. And v here, by the way, has the same magnitude. V has the same magnitude. The speed doesn't change. It's only the direction that is changing, okay? So we have acceleration, not due to the change in the speed, but due to change in the direction of the velocity. And the force here will be up, Fb. So at the end, you get what? Circular motion. Circular motion. This is when V and B are perpendicular, okay? We'll see later when they are not perpendicular what happens. So you get a circle of radius r, okay? Let's try to find the radius of this circle, okay? The radius. So what do we write? Fb, which is the magnetic force, is QVB. I hope you agree with me, yeah? QVB. What is the sign of the angle between V and B? Is 90 degrees, because V is for example, V is up here in this case, and B is out. What is the angle? What is this angle here? It's 90 degrees, okay? Similarly here, 90 everywhere, okay? And this, since we have a circular motion, this is Newton's second law, okay? But the acceleration is what? Is v squared over r, okay? That's the acceleration, the radial acceleration, huh? It's radial. There's a radial acceleration. Be careful here. The speed, let me write it down here. The speed is constant, okay? The speed is constant in this case. But the velocity is not. Velocity is not. Okay, very important. Why the velocity is not? Because there's a change in direction. Okay, the speed is constant, but velocity is not. So let's find r. What is r? R from here, it will be, so you cancel one of the v from here. R will be m v over q b. That's the radius of my circular path. Okay, it depends on the mass of the object, the q, the charge of the object, the speed of the object, and the magnetic field. Bigger speed will give you bigger radius, okay? Bigger magnetic field will give me smaller radius, and so on, okay? So that's so m is what? The mass of the particle. Be careful, that's the mass of the particle in kilogram, should be, okay? V is the speed of the particle, okay? The speed in meter per second, SI units. Q is the charge of the particle. Okay, the charge of the particle is a Coulomb, and B is the magnetic field, okay? The magnetic field in Tesla. In Tesla. If you use these units, okay, the R will be in meters, okay? Will be in meter. That's the units for the radius. It's a distance, okay? It's in meter. Now we can calculate what we call the period of revolution. The period, okay? Then the period of revolution, t, the period of revolution, t is 2 pi r, which is the circumference, over v. Okay, 2 pi over v. Distance over speed, that's the time. To make one revolution, the period is a time for one revolution, okay? It's a time for one revolution. Time for one revolution. Or one rotation. One revolution. So from here and comes back to here. So what is the distance here? It's 2 pi r over v. We said v is constant, the speed is constant. So be careful. Eh? So if I put r, this value of r here, if I plug this r here, what happened to this v and v will cancel, and you end up with 2 pi m over q times b. That's the period of rotation. Okay, let me write it down here. 2 pi m over q b. You notice something very important, that it is independent of what? Of the speed. Eh? The period doesn't depend on the speed. It depends on the mass, the charge, and the magnetic field only. We can also find the frequency of revolution. The frequency, okay, which is f, which is 1 over the period, which is q b over 2 pi m. We can also find the angular frequency. Angular frequency of the rotate of this circular motion, okay, which is omega, which is equal to 2 pi f. So when I put f, this value of f, the 2 pi with 2 pi will cancel. You end up with qb over m. So this is, of course, in seconds. This here is what? In hertz. And this is in radian per seconds or hertz. Okay, radian per second. Okay, that's the units of the angular frequency. And this is hertz or 1/seconds. And this is a period in seconds. Now, let me discuss with you something. What happened when the B, when B and V are not perpendicular, okay? When V and B are not perpendicular. So there is an angle phi between them, okay? Let's look at the example, the figure here, okay? Let me show you. This is B and this is V. You can see V is not perpendicular to B. It's not in the plane because B is vertically up. V should be in the plane, but here no. It has an angle between the direction of B and the angle is phi. So this V has two components. One which is perpendicular to B, which is responsible for rotation, and there's this component here which is parallel to B, which makes the object move in a helix. So the motion, in this case, the motion is helical motion. Huh? So you end up with a helical motion. Okay, that's it's circular in the plane, but there is a pitch, something called the pitch P. So we call this the pitch. The pitch is how much, for every rotation, how much it has moved with the direction of B. Okay, so B in this case, B is in perpendicular. Of course, this figure has to be careful. The radius is constant here. Okay, so let me keep it like this. So this is my B, and I have two velocities. One which is parallel to B, and one which is perpendicular to B. I'm going to draw it inside. Okay, V perpendicular. The V perpendicular to B will give you the rotation, and the V parallel will give you the translation of this circular motion. Actually, it's circular in the plane, and it is moving up. So the motion is, we call this one helical motion. Helical motion. Okay. So this is a case when V and B are not perpendicular, not like here. Here, circular motion when they are perpendicular, but here is we call helical motion. We have the pitch here, the distance between two. So there's a circle motion. At the same time, there's a motion along the B because of this component of the velocity. Now let's discuss. Let me give you an example about two particles. So this is finished now. Let me give you an example of two particles. One has a small circular motion, okay, and one has a larger circular motion. They have the same charge and the same mass. So same charge, same Q and M. Okay? So the Q over M ratio, or M over Q, is the same. So this one will have a radius R1, and this one will have a radius R2. The question, which one has a greater period? Which one has a longer period? Let's say longer period. Which we call this number 1. We call number 2. Which one has longer period? Okay, that's the question. Okay, but you have to remember these two particles, Q, they have the same charge and the same mass. Okay, same charge and they are moving in circular motion. It means the force, the V and B are perpendicular. I don't worry about that. I'm asking which one has a longer period. If you look at this period, the equation for the period, it says 2 pi m over QB, and also they are in the same magnetic field. Same charge and M and same B. So everything is the same here. The mass, the charge, and the B. Okay. So the question is, which one has longer period? The answer is what? They have the same period. They have the same period. Okay, that's the point. Why is that? Okay, they have the same period because they have the same charge, the same mass, and the same B. They are in the same magnetic field. Okay, so they have the same period. How come if they have the same period, and this is moving longer distance, they don't have the same velocity or speed? So which one has a higher speed? If you look here, since they have the same mass, same charge, and same B, the one which has which has bigger radius will have higher speed. So number 2, this case here has higher speed, and therefore, by having a higher speed, it will make this revolution in the same time as this one here. This one has a slower speed, and this one has a higher speed. Okay, so that's the point. Okay, this is important. Bigger radius means higher speed. You can see it here. Bigger radius means higher speed. I think this is clear, and I hope it is clear. This idea about circulating charged particles. We have circular motion when V and B are perpendicular, and we have a helical motion when V and B are not perpendicular. There's an angle phi between them, and that angle phi is here. This is V and this is B. You can see they are not perpendicular to each other. The V has two components, the perpendicular and the parallel. This parallel will make it move up, and the perpendicular will make it move in a circular motion. So you have two motions, a circular and a translation, and the whole motion will be what? Will be a helical motion. Okay, we said that the Earth, this is the Earth, it has a magnetic field, so it's like a bar magnet, which has this, the north of the bar magnet is the south, geographic south. This is south of the Earth, and this is the north part of the Earth. It's the south, the magnetic south. Okay, so you have a magnetic field here in green, as you can see, and there's a phenomenon. It's called the northern lights. Okay, I'm going to try to explain this phenomena. Before I explain it, let me show you what happened in this phenomena. You can see it here. You can see these are lights from in the sky. Okay, you can see them. These are natural phenomena. You can see them very clear. I hope they are clear. You can see colors in the like a wall. You see like a wall here, and it is colored green and different colors. Okay, I will try to explain this, what is happening. Okay, and that is happening always in the north and the south pole, where the magnetic field of the Earth is strong. It is stronger in the north and south pole. It never happened around this place, Saudi Arabia, or because the magnetic field is very weak there. You can see the colors, and this is a very beautiful phenomena. There are people who go to the north and south pole just to look at these beautiful sceneries. Okay, you see here different colors, green, orange, and so on. All right, now let me try to explain to you this phenomena, and later, if you can go to YouTube and write Northern Lights, you will get this kind of beautiful videos showing this phenomena here. Okay, so the Earth has a magnetic field, and the green lines here, the green lines are the magnetic field of the Earth. That's B. Okay, you can see the green lines are closer here, which means the magnetic field in the North Pole is very strong. There's something called something called the solar wind. Sometimes you get protons, charged particles coming from the sun. The sun is here, okay, and it is sending us these particles, protons, okay, and they are showering the Earth from time to time, okay, and this proton, they are charged particles. Once they reach this, when they reach the magnetic field of the Earth, they start, because V and B are not perpendicular, they start spiraling. Okay, spiraling. Okay, all these particles, they start spiraling, and when they spiral, they will ionize the air molecules. Okay, the air is made of oxygen, nitrogen, and hydrogen. Okay, very little hydrogen, but most of it is oxygen and nitrogen. Okay, so when they ionize these the atoms of the air, the atoms of the air, these particles, the protons, they ionize, then the atoms goes back to its stable configuration and emits these lights. Okay, so these lights are emitted due to the fact that the air molecules are ionized. Okay, and then they form what we call a plasma. Okay, and then they come back when the electron comes back to the atoms go back to its stable configuration. Then it emits these lights, and these lights are here because of the speed of these protons is high, because the magnetic field of the Earth is strong here and it is weak here. So whatever you do, you cannot accelerate them to make the collisions between the protons and the atomic the air atoms. Okay, atoms of the air. But here it is, the magnetic field is strong, and therefore the collision between the atoms of the air and the protons is strong, and they ionize. They have enough energy, those protons, to ionize the atoms, and then when the atoms goes back to its equilibrium, it emits those lights that you have seen. You can see more of them if you want. Here are those lights. These are coming from the air molecules. Okay. You can go to another light and see on YouTube and see these beautiful pictures there. As I told you, there are people who travel just to watch and film this kind of beautiful sceneries. Thank you very much.